Different chemical species have different abilities to attract electrons. So that's to do with their electronegativity. Some are more electronegative and some are less electronegative. The electrochemical series gives you a list of all of the ability to gain electrons or to undergo reduction reactions. And what we call their ability to gain electrons is their half-cell reduction potential, and that's measured in volts. So what we've done is we've looked at, here's hydrogen gas, and how well is everything to gain electrons from hydrogen, and we compare it to that. So they're listed in order of electron attracting ability, and that's compared to hydrogen half cell. And we said that hydrogen has an electron attracting ability of 0. So compared to hydrogen, can it attract electrons from hydrogen, or does it lose electrons to hydrogen? Which way is it? And so we give it an arbitrary or a value of 0. And these are the conditions. So it must be done at 25 degrees Celsius or 298 degrees Kelvin, not degrees, sorry, just 298 K, pressure of 1 atmosphere and concentration of 1 molar. And we're going to go through that, okay? So you might have seen this series before. This is in the data book. This is on page, I don't know, 3 or 4. It's right at the beginning. Yeah, obviously page 113 of our booklet, but this is in the VCAA data book, so make sure you're familiar with this. So here is hydrogen right in the middle. Hopefully we can highlight this one. So hydrogen's right in the middle there, and we're comparing everything to hydrogen. So if it can gain electrons from hydrogen, it's positive. If it can lose electrons from hydrogen, it's negative. So this one, anything above gains electrons from hydrogen. And anything below, down here, loses electrons from hydrogen. Page 2, yep. Yep, cool. Just go chats and back there. All right, so you need to know that. You don't need to memorize it, but you need to know where it is and what it means. So it tells you the energy in volts. They're all voltage because it says volts there. Okay, all V's all the way down. The energy produced when that cell is compared to hydrogen. So if you paired up fluorine and hydrogen cell, the fluorine would gain electrons. So electrons would go towards the fluorine gas, right, through an electrode there, and you'd have 2.87 volts of energy per mole of that. All right. So, yeah, I'll just go through a couple other terms. All right, so electrons go there. So if I zoom out a fraction, just to make it, so we can see the whole thing. Anything here, this accepts, as I said, electrons more readily. So it accepts electrons well from hydrogen. And that's why it's got a positive E naught. So E's naught value is positive. Whereas anything below, down here, it doesn't accept electrons less readily, meaning it loses electrons to hydrogen. And so therefore it's a negative E naught value. That E to the symbol, it's E naught, like E to the 0. E naught is just a measure of voltage. It's a measure of the energy that's coming in or out. So what we have here, going down the table all the way, and we'll go through that. I'll put in a different color so it's easy to see. We've got increasing, reducing strength, which means it undergoes oxidation. So it's getting stronger at undergoing oxidation, better able to go oxidation down the bottom right-hand side. And up the top, we've got increasing. What do you think? What would be the other term we put here? Increasing something strength. It's not reducing, it's going to be the opposite. Not reducing strength. It undergoes reduction better, but oxidizing is the word I was looking for. So increasing oxidizing strength, meaning it undergoes reduction better. So it's reduced. So top, anything above here on the left, I don't have the, if I do this, it might make it, I'm just going to do a quick, where's my, and I want to do the keyboard, the control. Where do I want? That one. Cool. Now I can get it. So up the top left up here, you can see that they gain electrons really well, so increasing oxidizing strength. Bottom right, anything here underneath hydrogen, they lose electrons to hydrogen, and so therefore increasing reducing strength. All right, we're going to move on from there. Oxidants left-hand side, reductants right-hand side. So that's, remember, undergoing oxidation, and this undergoes reduction. A reductant undergoes reduction, and a reductant undergoes oxidation. And as you move, they help you look at the oxidants and reductant strength and write redox equations. They don't tell you rate, so there's often questions about rate, so be careful. They don't tell you how fast they go. So this equation here, hydrogen peroxide going into oxygen and hydrogen, that can take 2 years to happen without a catalyst. So it can take a long time for this to degrade into oxygen and hydrogen ions. Or the, where's the other one that I wanted? Yeah, anyway, so it's a very slow process. No indication of rate. All right, let's do some examples and this is where the important stuff is. Okay, so list the following in weakest to strongest oxidant. So we go back, and it is confusing because oxidant means undergoes reduction, but causes oxidation. So write out the term. We might have only just seen the term or just familiarizing ourselves with the term here. Write out the term, and then from there, we're going to look at which of these would be the strongest oxidant, so best able to undergo reduction. So it's got all the species: water, hydrogen ions, sodium ions, and copper. So we go through and we highlight them because it's probably easier to do that. I'm going to zoom in. So water, we've got a few waters. I'm just going to go, so sodium ions are there. Is that going to let me highlight? Not too well. I'll use the pen, and let's go like a light color. So there's sodium ions there. What other ions do we have? We'll go through what impacts the rate a bit later. There's a few things. See energy in that. What else do we have? Copper. So copper's here. So circle or shade or highlight all the species. So find that. What else do we have? Sodium ions. That's not going to get rid of it, is it? No, it's just going to get rid of that. Yeah, okay. It's all good. What else do we have? Hydrogen ions. Yep. So there are a few places of hydrogen ions. We're just going to use the hydrogen ions which are at the 0 voltage. So this one here, these hydrogen ions. Because there are a few. There's hydrogen ions elsewhere, but you need other things for them. Like your hydrogen ions here, but we're just talking about these ones down here. The last thing, what else do we have? Water. So there's water here, but it needs oxygen in this case. So we can't use that one. You need oxygen for that equation, so we're not doing that equation. Okay, you've got water here as well. That water can react, potentially. There's water here. There's also water down here. All right, so there are a few different examples of water. So we want to say which one undergoes reduction, which one can be reduced. And it's going from weakest to strongest oxidant. So what would that be? What would be on the far right, would you have the one that gets reduced more or the one that gets reduced least? So one that gets reduced least? Is that what you're saying? Yeah, more. So the most able to undergo reduction is on the right-hand side, and the least able to undergo reduction on the left-hand side. That's what we're talking about, okay? So the most able, or the thing that can best undergo reduction, would be anything up to the top. Is that correct? Anything towards the top can best able to undergo reduction? Yeah, it depends on the side. So remember, up here, these undergo reduction. Anything on the top left and anything on the bottom right undergoes oxidation. And reduction increases up here. So in this instance, the water is on the wrong side. The water is on the wrong side. So the water actually can't undergo reduction. It's already reduced in this instance. Water can't undergo reduction. Because remember, reduction is a gain of electrons. And so if you went that way, you're actually losing electrons. That's a loss of electrons. So that can't be gaining electrons, so it's not reduction. They're already reduced. These waters are already reduced. This water can be reduced, but it requires oxygen. So it can't work without oxygen. So we cross that one off as well. That's not the equation. This copper is already reduced. It can't be reduced. So the only one that can be reduced or most able to undergo reduction is actually hydrogen. So hydrogen here is the most able, the highest ability to be reduced. Then the second one is this water at negative 0.83 volts. So this water can be reduced next, and then only then will sodium be reduced. The sodium is the lowest or least likely to undergo reduction, then water, and then hydrogen. I'm going to put the voltages underneath just so you know exactly when you come back to it. Negative 2.71, negative 0.83, because there are a few waters, and then 0.00. Volts, volts, volts. So that's how you would do that problem. Yep, copper can't be reduced. Copper is already reduced because it's already a copper solid. So remember, copper is already in the reduced form. Can't gain electrons. If it was copper 2 plus, if it was this, then yes, copper would be the strongest. On the far left, no, because it's already reduced. Yeah, it's relative. You're right, it's relative, but it specifically said oxidant. So copper is not an oxidant. And the same thing this year, they had a question where you had on the exam, last year, fluorine can't be reduced. So fluorine is actually not an oxidant there. It can't be reduced by anything else. So you can't say it's a stronger oxidant or stronger reductant is what I'm saying. Right, so no, it's not correct to put copper there because copper can't be reduced. So it's not an oxidant. All right, we're going to go through, it's a difficult question, so we're going to go through it again in another format. Here, number 19. I think I've got a poll for this one. I think I put that in. And then we'll do spontaneity, and then we'll have a break. Okay, so we've got 2 more pages, then we'll have a break.